Hello, everyone. I just wanted to do a quick introduction of myself. My name is Ashley Herbst. I am a PhD candidate at Arizona State University in astrophysics. I do research in a few different areas, but overall, my interests lie in the formation of our solar system and the many different ways that we study that. So one important way is to utilize meteoritics in kind of incorporating really nice solid data points into our modeling. And so we use meteorites and pre-solar grains to really study the not only formational processes but the evolutionary processes of our solar system. And then in the future, hopefully, a lot of that work can be extrapolated to other exosystems. So I'm very excited to be here and to be your instructor. Okay, so a really quick lecture outline. We are breaking this lecture up into 3 different parts. One is a brief history of astronomy through Ptolemy, which should introduce the scientific method, and geocentrism, which is basically the Earth in the center of the solar system, or as they would have thought, the universe. Revolutions in astronomy, we'll talk about Copernicus and heliocentrism, Tycho, if you really want to be Dutch about it, Tycho Brahe and Johannes Kepler. And then we will do a quick discussion on what is astrobiology, and we'll introduce the Drake equation. So astronomy really is one of the oldest sciences out there. We say this because it is, way back when science, the term science and what we think of as science with the scientific method wasn't really figured out quite yet. But people were making observations of their surroundings, and one aspect of their surroundings easily observed is the sky. You can go outside tonight, tomorrow, throughout the whole week if you want, and you can observe the night sky. You can observe the stars, not so easily in the Phoenix area, but we'll just pretend that it's really dark outside. You can go out and you can easily observe and notice any sort of changes in the sky. You can even do this during the day. Just don't look directly at the sun. So that's why astronomy was a very easy science to get into, because it was easy to do these observations. And so this is why many early civilizations with texts or manuscripts that survive wrote about their observations of the night sky. And so astronomy, again, is really one of the oldest sciences. These observations of the sky are important, particularly for us to understand these civilizations, but for people within these early civilizations, because they based a lot of their agriculture on, when the fall weather was supposed to happen. And you can kind of tell that when the sun is in a certain point of the sky. The moon as well. You can use the moon to tell time and figure out your calendar. People used astronomy to navigate the globe. So astronomy is not only an old science, it's actually a very practical one. And so as, someone who can relate to maybe these early peoples that would make these observations of the night sky from night to night for a certain amount of time, you too would notice a very regular and predictable motion and perspective of the sun, moon, and stars. For example, if you're looking at, the image on the right-hand side with the star trails, this is probably over, maybe 12 to 24 hours. You can kind of see that the trails of the stars are constant, and they make a very consistent path around what is at the center of the star trails, which would be Polaris, our North Star. So this is in the northern hemisphere. And night to night, this is what you would see. Now, if you were to observe longer, let's say you go out one night during the warmer months of the year and you notice that the sun is setting really late, and then you notice this is different about 6 months later during the colder months where the sun is setting earlier in the day. That may seem different, but then given year to year, you notice that there is also that particular trend. And so these observations with these regular and predictable movements from night to night really help us, or really helped especially the early people, develop a model of why this was the case. So what you're seeing here is a logical outline that scientists go through when they are doing their science. We generally tend to call it the scientific method. And so this scientific method starts with an observation, which is great because as people, we make observations all the time of our surroundings. And then we also generally tend to ask a question about one of those observations. And so this is what scientists do as well. They go a step further in answering their own question, which is formulating a hypothesis. And then they test this hypothesis by gathering data, performing experiments. And once they do that, then they see if the answer is falsifiable. And so generally we tend to either reject a hypothesis or we can't falsify it, so we continue to test it and we continue to probably refine and expand on it, because as you can see, this is a circular model, and so you're never really done testing and refining your hypothesis. And then you're always reporting conclusions, even when something is falsifiable. So we'll start as if we are in, Greek antiquity, looking at the night sky and making an observation. And our observation is that the sun and stars have predictable motions across the sky. So night after night, we are observing where the stars are at, maybe with noticeable constellations. We go out during the day and we also see where the sun is at. And we chart that night after night, day after day. And we see that we can predict where the sun is going to be, maybe in the next week. Or where the stars are going to be, a couple months from now. So that is our observation. And so logically, our next step is to ask why. What causes these motions? What causes the sun and stars to have predictable motions across the sky? So thinking about Greek antiquity, and the knowledge that they did have, the assumptions that were made, which is very important in science when someone is, testing a model. It's always good to know what kind of assumptions are being made. And so at this point in time, when we're talking about Greek antiquity, we're talking about, BC, like maybe, 200, 300 BC. And so an assumption that would be made is that the Earth is round. That has already been proven that the Earth was not flat. And then it would also have been assumed that the Earth is not moving or rotating. The thought is if it were, Anytime an object left the surface of the earth, a bird in flight, tossing an object into the air, etc., the earth would move below it and the object would get left behind. This is obviously without a good understanding of inertia. That would come later. So these are the two assumptions that are being used by the people of the time to try and answer this question of what causes these motions. And so with these assumptions, trying to answer the question what causes these motions, a hypothesis is formed, and that would have been objects in the night sky, like the sun and stars, must rotate around the stationary Earth. And you can understand just going outside night after night, even in, really bright Phoenix, you can understand why people of antiquity would have thought that the Earth is at the center of our system and not the sun. It's not very apparent that the sun is. And so this is kind of the primordial hypothesis of the mechanics of our system. And so this model is called the geocentric model. This geocentric model, most importantly, puts the Earth at the center of what the Greeks or any really early persons would have called the universe. Didn't really go much farther than that. They thought everything that we see in the sky is basically how it's drawn. So you have the Earth at the center. You have everything else in their own individual spheres moving around the Earth, including the sun. And then the stars, which seem to move at the same speed night after night, are placed on this what's called a celestial sphere that also moves around the Earth. And so this early version is attributed to Eudoxus. But it's really refined by Aristotle, and if Aristotle says this is so, then it must be so. It was very difficult to get away from this geocentric model, and it really stuck around for a very long time. And one more thing I would like to add about having all the objects moving in circular spheres, philosophically, to especially the Greeks, they thought the circle was perfect and the heavens are perfect. And so the 2 and 2 coincide. So it must be circular orbits around the Earth. So here now I just kind of want to reiterate. We started with the observation of the sun and stars have predictable motions across the sky. The question was then asked, what causes these motions? We know about the assumptions that were made by these early persons, the hypothesis that came from the assumption, objects in the sky must rotate around the stationary Earth. The prediction is that all objects in the sky should always follow regular arced paths. And so this is what we are testing. And it took a long time to test this, but gathering a very long time and a good amount of data, the sun, moon, and stars all appear to follow regular arced paths through the sky. However, there is something that needs expounding on, and that is that the planets sometimes don't follow this regular arced path as well. So that is something that actually has to be refined. So this hypothesis is somewhat falsifiable because the planets do not follow these regular arced paths. And so when Greeks would go out at night and look up, they saw stars, they saw constellations. So these are, figures like Pegasus that are made up of a grouping of stars. And they noticed that there were a few stars that seemed to move faster night after night than the background stars. And so these quick moving stars they named planets, which is a word that is derived from the Greek word for wandering. So these wanderers also seemed to follow the same line across the night sky. So they weren't really scattered like the background stars that you see here. They actually followed this blue line in the image called the ecliptic. And this ecliptic is the sun's path. And so not only do the planets follow this ecliptic line, but so does the sun, and so does the moon. And another name for the ecliptic is the zodiac. And so very close to this blue ecliptic line, you can see constellations that probably sound very familiar, like Pisces or Aries, Aquarius, Capricornus, or what we would call Capricorn. And so these are the zodiacal constellations, and the Greek thought they were very important because the sun's path moved through them. And this has stuck with us to the present day as zodiacal signs. So let's remember a hypothesis. So the hypothesis that the early peoples thought was that these heavenly things, the stars, the sun, the moon, the planets, all move in a very predictable circular arc. And that means that they all move eastward. So what I'm saying is, like, if you were to go outside and you were to look up day after day, you would notice the sun rising in the east and setting in the west. Really quickly, we now know that this is due to the Earth's rotation. That is something that was not known in early antiquity. So the early Greeks, Romans, they would not have known this. But if we were to turn off this rotation, the Earth's rotation, we would see the stars and the planets moving eastward night by night, so west to east. Sometimes planets, not stars, will change their direction they are moving from west to east to west, like the rising and setting sun when the Earth is moving like on its own axis. So this wandering eastward from west to east is called prograde motion, and the planets do this as well along the ecliptic, but sometimes they don't do that. They move westward from night to night, so they actually will look like they'll be going east west to east night after night, and then all of a sudden they look like they're actually now starting to move westward night after night, so from east to west, and that's called retrograde motion. And this happens on fairly large time scales, but not large enough to where they're not observed. And these periods of retrograde motion really cause an inconsistency with the hypothesis that planets move in a circle around the Earth. So that means our hypothesis is falsifiable. Because we were able to falsify our hypothesis that the sun and stars rotate around the stationary Earth in a regular arced path, we now need to refine, expand, or just completely reject the hypothesis. But we really want to answer that question of what causes these motions. And so what the people of antiquity did was they decided to refine their hypothesis. And one way they decided to aid in their refining of their hypothesis is to add a third assumption. And that assumption is the motion of the sun, moon, and planets around the earth must be in perfect circles. And so not only regular arced paths, but the earth, again, is stationary at the center, and everything around it is no longer moving in this, perfect circular sphere around the earth, but they're actually moving in circles around the earth. And we'll see what I mean by that in the next slide. And so this is called the Ptolemaic model. The Ptolemaic model operates under the assumption that the planets move around the earth and that all motion must be in perfect circles. And recognizing that sometimes the observable planets move in a retrograde direction. And so looking at the image on the right-hand side, you notice that, again, the Earth is still somewhat at the center of this system, but no longer do you see those circular spheres around the Earth containing the planets, the sun, and the moon. You now see circles around this larger circle around the Earth. And so this is called an epicycle. So the planets move along a small circle called this epicycle, and this epicycle allows for this retrograde motion. So this is one way to try to explain what we're observing. And so the epicycle, again, moves along that larger circle called a deferent. And again, notice they are perfect circles. Thanks to the University of Nebraska at Lincoln, we can watch a video of what this would look like. And so let's get this started. So you'll see that there is at the center an Earth, a circle around it, and then you start to see this planet, we'll just go ahead and call it a planet, in an epicycle that is cycling around the Earth. And you can see that this allows for this tiny loop that occurs, and that is retrograde motion. So the planet is performing a prograde motion until it makes these little loops that are retrograde motion. And this is a nice way to try to explain what's being observed with the assumptions that we have for the time. And so now, with epicycles and deferents, we have refined our hypothesis to include them. And so this is the newest way, after Aristotle, to explain the motion, the predictable motions across the sky for the sun and moon and stars. And as this task says, report conclusions, Ptolemy did report his conclusions about his ideas of his new geocentric model, which of course were published in Latin in 1528, centuries after Aristotle and his geocentric model. All right, so now we will move on to the next section in this lecture, which is revolutions in astronomy. So there was the idea of geocentrism, where the Earth is at the center of the system, of the universe for these people. But there were people who also thought the Earth was in a heliocentric state with the sun at the center, instead of that geocentric state with the Earth at the center of the universe. The first person to probably propose this was a guy named Aristarchus, who was an astronomer, mathematician in the 300s to 200s BCE. he calculated the relative sizes of the sun, earth, and moon, and logically found that if the smaller moon goes around the larger earth, then the smaller earth should go around the larger sun. And that makes sense. And when you put the sun at the center, you can easily explain retrograde motion with geocentrism and epicycles. They started to find that it wasn't just one epicycle, but it was epicycle on top of epicycle to try and get the Ptolemaic model to work with what was being observed. So this was the birth of heliocentrism. It just didn't really take hold. It probably took a lot more thought for this idea to really take hold. And the geocentric model just made sense when you were just looking night after night. But then you start to take the retrograde motion into account, and you find that the sun at the center really works out. So the first to famously put forth a sun-centered heliocentric model apart from a geocentric model is Nicholas Copernicus. He was aware of Aristarchus's work, except he couldn't quite get rid of the idea of perfect circles from the Ptolemaic model. And so he took the idea of perfect circles, but he put the sun at the center instead of the earth. And you can see that it's not epicycles anymore. Everything has their perfect circular spheres, but around the sun, including the earth. This was good in that the sun was at the center. However, because of the circular orbits, couldn't quite predict planetary motion very well. But his work is published, and so this hypothesis held for a little bit until planetary motion started to, kind of muck up things again. The next person important to this story of early astronomy is a man called Tycho Brahe. He is a very interesting person. Few fun facts. He wore a brass nose because he was stabbed in the face. He was of nobility and very wealthy. He also threw a really elaborate parties where he got a hold of one of the king's elk from a forest that the king owned. He got it really drunk, and it famously fell downstairs during this party. He was also given access to an island for his astronomical observations, and he assumed that the island was his to the point where he taxed its inhabitants. To say he was eclectic is a severe understatement. But we are also very lucky that he had an interest in astronomy, because though he didn't really do a great job at interpreting his data, he was very good at gathering accurate, even precise astronomical data. And this data is very important in that it is used as a tool for an apprentice that Tycho Brahe had. And this apprentice is famously Johannes Kepler. And Kepler was fairly opposite of Brahe. He was a part of German nobility, but was impoverished. He loved astronomy, and as a child, made observations of his own, but couldn't continue those observations due to poor eyesight from when he had smallpox. He had always enjoyed mathematics, and so he was able to take this ability and combine that with Brahe's accurate observations to propose a heliocentric model where planets orbit the sun. So if you look at the image on the left-hand side, you can see the Copernicus model where the sun is at the center, but everything is orbiting in perfect spheres around the sun, so perfect circles, still reigning in this model. But then when you go to the right-hand side and you look at Kepler's model of the orbits of these heavenly bodies, you see the sun is at the center, but no longer are they perfect circles. They are now ellipses. And these ellipses would revolutionize the idea of how our solar system, or at this time the heavens, the universe, how its mechanics work. So this is one of the best models to come out of centuries of refining and expanding on this early hypothesis of the Earth being at the center and everything orbiting the Earth in perfect circles. So the last section of this lecture is what is astrobiology? Before we begin, go to the discussion boards in Canvas and tell me what you think extraterrestrial life is in your own words. You can draw pictures even. There are no wrong answers. Just put some thought into it. And I'll be excited to see what you say. Okay, so, what do you think of when you hear the words extraterrestrial life? For me, I think of the possibility of, little single-celled organisms trying to make it in some, extreme environment on some planet far away. It's a really fun idea. By definition, extraterrestrial does mean from beyond Earth. In pop culture, they are often portrayed as intelligent life forms, typically humanoid looking because we are humans. But in reality, scientists only know about one kind of life, and that is here on Earth. So we have one data point of what life is. So extraterrestrial life could be single-celled, like I kind of wonder. It could be multicellular, or it could even be something that is severely unknown, something that is very different from life as we know it here on Earth. So by learning more about the solar system and even other solar systems in our galaxy, really systems, solar system is for the sun, but other systems in our galaxy, scientists are also learning more about the possibility for life beyond the Earth. And so astrobiology really is a very interdisciplinary science. It incorporates knowledge from astronomy, geology, chemistry, and biology. If you're looking at this Venn diagram, they all kind of converge into astrobiology. And so, astronomy can be thought of as like, what is the universe made of? What type of stars and planets exist? How is all the stuff in the universe arranged, and how does it interact? And in reality, astronomy is not limited. It is the universe. Everywhere experiences gravity to a certain extent, the laws of thermodynamics, etc. So the laws of physics. If we look at chemistry is like, what types of elements, molecules are necessary for life as we know it? What about for life as we don't know it, which is a very important question too? And what chemical reactions may have contributed to the origin of life? And so chemistry is rather limited to planets and even to the cold regions between stars known as the interstellar medium. Chemistry is mostly phase changes and bonding that can occur in regions not dominated by plasma or by stars. And so chemistry can be applied to the cooler or outer regions of stars, but then you're kind of starting to get back into the ISM. And so same really applies for geology as well. So if you look at geology, some of the important questions are like, what types of environments exist on different planets? How do those conditions support the origin or evolution of life or not? What surface processes impact the origin and evolution of life? And how do conditions change over space and time? And so geology is really limited to small objects on an astronomical scale, whether that be planets or even interstellar dust. And a lot of my own personal research is a great mixture of astronomy and geology. I do have a background in geology. And so the last thing is biology. And biology is like, what is life? What are the requirements for the formation of life? And how does life change or evolve over time? And even harder to answer, how do we define intelligent life and how does it develop? And so biology is even more limited in that it is only observed on Earth. It is the only place that science, or that biology has ever occurred. One thing that's very commonly studied here at the School of Earth and Space Exploration at ASU is planetary science. And planetary science is basically like, what do we know about the bodies of the solar system, planets, moons, asteroids, comets? Could life have existed on other planets or moons in the past to an extent? Could there be life there today? So planetary science is kind of like a subset of astronomy and geology, but also chemistry as well. And so where and how we look for life depends on what life is. And that is probably the hardest question to answer. And so where and how do we look for life kind of depends on where we're looking first. So the first place that we've been looking is in our own solar system. So in our own backyard, whether that be other planets like Mars, moons of other planets, quite a bit, around Saturn, or possibly even Jupiter. Studying the chemistry and geology of these places. And then we're also looking for evidence outside of our solar system too. So exoplanets are a big topic in astronomy, astrobiology. Exoplanets kind of converge on many disciplines. And so there's also technological signs of life like radio signals, or chemical signs of life like detecting certain compositions in planetary atmospheres. These are all very hot, current places of research within astrobiology, but also astronomy, chemistry, biology, and geology. And so to put all of these variables together for trying to find life out in space, one way that has been thought of is called the Drake equation. And the Drake equation is a model for estimating the number of detectable alien civilizations that currently exist in our galaxy, which is defined as big N. I wouldn't say this is so much of an equation, maybe more of a bunch of statistical limiting factors for finding this detectable alien civilization. So for this equation or statistical limiting factors, we're trying to figure out all of these for big N. And so our star is representing the limiting factors for star formation rate. And then the next one is F sub P, which is a fraction of stars that have planets. Let's see if I can use the, it's very stuttery, so I might not be able to. Let's see, there we go. So the next one is F sub P, or a fraction of stars, or what fraction of stars that have planets, and what are the limiting factors for this. And then N sub E is the number of Earth-like habitable planets per star system. And then you have F sub L, which is a fraction of Earth-like habitable planets where life develops. And then we continue on. F sub I, fraction of Earth-like habitable planets that life evolve, intelligently. F sub C, fraction of intelligent life that develops into a communicating civilization. Finally, ending with big L, which represents how long a communicating civilization lasts. And so you can kind of see that we're getting from, something really big and possibly well understood to something that is not really well understood and very hard to answer. So the first three limiting factors within this Drake equation are astronomical terms, and these are pretty well understood, especially the first two terms are fairly understood. These do have actual values attached to them because we have been able to, based on our technology, accumulate data for these terms. So for F sub P, which is the second limiting factor, these stars with planets have been studied by telescopes like Kepler or TESS. TESS is a Transiting Exoplanet Survey satellite. And for example, TESS has, as of July of 2024, found 7,200 candidate exoplanets, of which 482 are confirmed. For N sub E, if we are going to be, very optimistic, we could say this number is 100% because statistically it is plausible that each star has a habitable zone with a planet. However, the issue here is that this is essentially the number of Earth-like planets, and we don't know what it precisely means to be Earth-like. That is the major issue with N sub E. So the first two factors we understand fairly well, and we even have quite a bit of data. But then things start to kind of become a little murky when we get to this factor. So what does it mean to be Earth-like? Do you have to have a moon? Do you need to have a Jupiter-sized planet in that star system? Does your sun have to be as close to our sun as possible? Does it have to be in a part of the galaxy like the Earth? The Earth is in an arm of the Milky Way galaxy, very far from the radiating center of the galaxy. That could be very important. So this is the first variable. Again, this N sub E is the first variable where there is a giant range of possibilities. We know how many stars there are, and we know that there are as many planets as there are stars. Next, how many of those star systems have Earth-like planets? And this is where things can go fairly wild. And so the next two variables are biological terms. And so F sub L and F sub I can be considered not astronomical terms, but biological terms. And F sub L is fraction of Earth-like habitable planets where life develops. So for F sub L, if you have a perfectly habitable Earth-like planet, does it actually have life, or is it barren of life? So F sub L is sort of independent of N sub E. We don't know how likely it is for life to rise up even on a habitable planet. If there are 1 million Earths out there, this F sub L term will tell us if there is one that has life or all that has life. If F sub L tells us it is really rare to have life, then even having 1 million Earth-like planets cannot guarantee life on all 1 million Earth-like planets. And then for the next one, F sub I, so fraction of Earth-like habitable planets with life that evolve intelligence. That means what is the likelihood that life will reach intelligence? And so these last two terms are sociological terms. And so F sub C is a fraction of intelligent life that develops into a communicating civilization. This variable indicates the likelihood that the intelligent life from F sub I will be able to send communicating signals into space. Frank Drake, the man you see in the image, was a radio astronomer, and he wanted to try to account for how many alien radio signals he should hear, which is why this Drake equation became a thing. While he was at Cornell, he thought maybe he could hear hundreds to even thousands of individual radio signals from possible galactic civilizations while observing with the university's radio telescope. But when he would do his observations, he basically came into radio silence. So F sub C is a very hard term to really rectify. And so then the very last variable, if everything else, every limiting term is well understood, the last variable is L, big L. And so that's how long a communicating civilization lasts. And one thing that could really need to think about is, so L is a variable that describes the length of time that the civilization lasts. And if a civilization on the other side of the galaxy lasts for about 1,000 years and puts out radio waves at the very beginning of their civilization, which is probably not realistic, but let's just pretend, we will not detect those radio waves before the collapse of that civilization. So there's a lot of factors that really depend on each other for this Drake equation. And again, it's very fascinating. So I'm very excited that we get to talk about this for these 8 weeks.